our last class we have studied digital frequency meter which can measure the frequency of a square wave. Okay. So, the input was a square wave which was applied to the clock input of a counter. That is how it works. So, that was measuring frequency of a square or rectangular wave. Now, let us ask a more general question. Can we measure frequency of non-square or non-rectangular waves like sine wave or other non-rectangular okay. So, can we do that? So, note that a counter it is a digital circuit, digital electronics element. So, therefore, it understands only logic I mean logical in high and low input. Okay. So, instead if we give a sine wave which is like this, it is difficult to say exactly what is going to happen if we give this input to a digital counter. Okay. It may even work, it may not even work. So, we are not going into that argument depending on the situation. So the let us assume, let us take it for granted that a digital counter works reliably or predictably only if the input to it is a rectangular square wave with logic level high and low. I mean okay. So, this sine wave we should not give directly to the counter. Let us take this as granted. Okay. Then what we have to do? We have to somehow convert this sine wave into a square wave with same frequency, and then we will give it to the counter. So, this is the sine wave. Okay. So, we will convert it into a rectangular wave with same frequency, that is important. So, say we will do it like this. Here it is 1, here it is 0 and then 1 and so on like that. Okay. Or yeah, so this is of same frequency, this is important. Now, we can give this square wave to the clock input of our counter here, and then it will count the number of edges and that will give us the frequency, right. So, now the question is how to convert a sine wave into a rectangular wave. Okay. So, we need to convert the sine wave into a rectangular wave with same frequency okay. But the question is how? And let us first try a very simple scheme. The scheme is this, just use a comparator. Okay. So, we may use a comparator. What is a comparator? We have studied this. This can be a op amp like this, okay, and it has two inputs. So what we can do, we can connect one input, say, to the ground. So this is the -1 inverting input, and say this is the positive, this is the non-inverting input, and here we apply this sine wave. Now how the output will change? The output we know of an op amp depends only on the difference between these two inputs, Vp and Vn. When Vp is higher than Vn, the output is positive and is equal to this positive supply plus V supply, and if Vp is less than Vn, then the output is equal to minus V supply. This is what we know, right? Now this Vn is constant, Vp is varying. That means when this Vp, this input, will be higher than 0, because this is always at 0 volt. So when input will be higher than 0, the output will be positive, and when the input is less than 0 here, the output will be negative. So this will become a square wave, right? Okay, square or rectangular wave. So when Vp is greater than Vn or 0 volt, output will be positive, and else it will be negative or 0. Okay. You may also ask, okay, this is plus minus V supply. But here I have drawn it as positive and 0. Let's keep that question also aside. Okay, these things you think yourself, these small questions, if you think yourself, the course will be more fun, more enjoying, and we can discuss this in forum. Okay, so this is a way to convert sinusoidal input into square wave or any other periodic signal, not maybe any other, but maybe triangular wave or sawtooth wave, this, or maybe this. All this can be converted into square wave. Okay, but there is a problem. What is the problem? The problem is that if the input signal, the sine wave, is noisy, then we will run into trouble. What do we mean by a noisy input? Say this is our sine wave. This is a perfect sine wave. Okay, although my drawing is not perfect, but assume this is a perfect sine wave. But now say there is some noise which is added to the signal, and therefore, so there is some small noise which is making it like this. Okay, so this is a noisy sine wave. Depending on the amount of noise, if the noise is bit high, then what can happen? Just consider this part. Let's zoom in to this part. Okay, so what do we see here? So we see, so this is the point where I am zooming in. So the sine wave should have been like this, but instead here the wave is like this. So what do we observe? We observe, so this is the actual wave, the blue one, and it is crossing the level 0. So this is 0 volt. So this line is 0 volt line. This is crossing the 0 volt line a couple of times, here once, then here, then here. So if we give this noise input to this comparator, how will the output look like? The output, okay, so the output here will be positive. So this will be the output. In this small region it will be negative, and then again in this small region it will be positive, and then again here it will be negative, and so on. So this is the output from the comparator. Okay, so this blue line is the input to the comparator or op amp, and the output will be like this. In this region, see, so before this point it's positive, okay, that's fine, as expected, as wanted. Here it goes to negative once, then it goes to positive again, then it goes to negative once, then it stays at negative for a while up to this. Okay, so you see that this is how the output is. But how do we want the output to be? The desired output should be like this. So from here to here it should be positive, and then it should be negative from here to here. Okay, so this is the desired or wanted output, but this is the actual output. What is wrong with this? What is wrong is that we have extra negative edge. So one negative edge, another negative edge. So observe that we have two falling edges. So that means in this part, when this part of the signal comes, the counter will be incremented by 2 instead of 1. But we want it to get incremented by only 1, because this is 1. So like this signifies 1 clock cycle, but here we will get a count of 2, an extra count. Okay, and depending on the amount of noise in this transition region, we may have more and more such false edges. So this is not good. We will get unwanted falling edges, unwanted negative edges, which will increase the counter more than the frequency of the unknown signal. So this is the problem, right? So I hope the problem is clear to you. Because of this noise, we will have unnecessary, unwanted falling edges, which will give higher value of frequency. Okay. So what is the solution? Solution is use of a Schmitt trigger. Use a what is Schmitt trigger? Okay, let us now talk about what is Schmitt trigger. Okay, so we will first talk about it functionally. How does it work? How does it function? Then we will talk about how it is implemented using op amps. Okay, so first function. So the symbol of a Schmitt trigger is like this. like a op amp, and inside the op amp you draw a hysteresis band or a hysteresis loop like a BH curve. Okay, so you know this is, so you know a BH curve for a iron or magnetic material, it looks like this. Draw this symbol inside. Okay, so this is what is the symbol of a Schmitt trigger. Okay, we will also understand soon why this hysteresis loop is inside. We will also understand that. Now, if you give an input to it, it will generate a kind of square wave or rectangular wave. How? Say the input is like this. So, this is input, this is output. Let me take a sine wave. Okay. So, this is input, this is time, this is 0 volt or input equal to 0. A Schmitt trigger has two voltage levels defined as the upper trigger point and lower trigger point. So, this some voltage level, maybe 1 volt, 2 volt, some voltage level is called or is or acts as a upper trigger point. So, this level, maybe this is equal to 1 volt, is called UTP, upper trigger point. And similarly, we will have LTP below this 0 volt. Normally, if UTP is 1 volt, then this is minus 1 volt. If this is 5 volt, then normally it is minus 5 volt. So, this is lower trigger point. Okay. And the input is varying like this. So, it is going beyond the upper trigger point and beyond the lower trigger point. Okay. Now, output, let me draw it here. Okay. So, this is output. Whenever the, okay, so let us start with some assumption that the output is initially negative. Okay, it depends on the previous history, it depends on what happened previously. So, let us start with the assumption that initially at this point at t equal to 0, the output is negative. Okay. Then the rule of this Schmitt trigger is that output will become positive when the input goes above UTP. Okay. So, the rule is, let me write the rule. Output will become positive when input goes above UTP and output will become negative when input goes below LTP. So, this is the rule, and elsewhere otherwise the output will retain its value. Okay, so at this point, you see, at this point here, the input is going above the upper trigger point. So therefore, even if the output was previously negative, at this moment, output will become positive, right? And then it will stay there. How long? Until and unless the input goes below this point, below lower trigger point. Okay, so until this point it will remain positive, and then at this point it will become negative again. Okay, so the output is not going to change here. Note that output is not going to change at the moment when input is coming below upper trigger point. No, at this moment output is not going to change. Even at this moment when output is going below 0, sorry, input is going below 0, output is not going to change here. Not even, not here, not here, only here. When the input goes below lower trigger point, output goes to negative. Then it will stay here. How long? Up to this point, when input goes above upper trigger point again. So it will not change here. Even if the input is going or crossing lower trigger point, no, not here, it will not change here. It will not change here when the input is going from negative to positive, no, not here, but only here. Okay, and then it will stay positive until it crosses the lower trigger point again. Okay, so for a normal comparator, okay, so for a normal comparator which we used before with an op-amp, output depends only on whether the input is positive or negative. So it compares with only one value. In this case, this is 0 value. So this compares the input with only one voltage level, which is 0 volt. This one compares the input with two voltage levels, upper trigger point and lower trigger point, depending on the current value of output. Okay, so I may also write a few more words. Okay, so this is the rule actually. So if output is already positive, then compare input with, can you guess? Can you guess? This is lower trigger point. If the output is already positive, then compare the input with lower trigger point. Okay, so like here in this region, consider this region. So here this is positive output. So now whether to change the output or not, that will be decided by comparing the input with the lower trigger point, not with the upper trigger point, not with the 0 level. Okay, so here we are continuously comparing the input with the lower trigger point. Is the input lower than lower trigger point? Here? No, 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 not even here. No, 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 no. Yes, here. So here we will change the output from positive to negative. But once this is already negative, then this lower trigger point is of no use. This is of no significance. This level 0 is of no significance. Now we will compare the input. Starting from here, we will compare the input only with the upper trigger point. So if output is already negative, then compare input with what? Upper trigger point. So this is how this Schmitt trigger behaves. Okay. Now let us see input output diagram. Okay, input output curve for a Schmitt trigger. So what I will do, I will draw input versus output. So this is input, this is output, and the output can be either positive V supply, or minus negative. Output can be either positive or negative. It will not take any value in between this. Like a op amp, like a comparator, I mean like a op amp used as a comparator, output will take only this value or this value and no value between this. An input that can take any value, that can take any continuous value, positive or negative. Okay. So now let us see how the output will change if we change the input. Okay. Say the input is changing like a sine wave, okay, or maybe a triangular wave. Let me do it here. Okay, so the input, applied to this Schmitt trigger is like this. It increases and then decreases, increases and then decreases. It's a triangular wave input time. So let me also draw this by rotating this this curve. So let me draw time here. So this is t time, and this axis here I will draw the input. Okay, so it's turned. So it's now changing like this, increasing, decreasing, increasing, and so on. Okay. Now how will the output change? So output changes depending on the comparison between input and the upper or lower trigger point, we know. Okay. So this is the rule. Okay. So it compares the input with upper trigger point or lower trigger point. So this point is, this line is like 0 volt. So this is 0 volt, and somewhere here I can draw the upper trigger point UTP. Somewhere here I can draw the lower trigger point LTP. Okay. So it will compare the input with these two levels depending on the current value of the output. So let's assume initially, once again let's assume initially the output is here. So at t equal to 0, the output is negative. This is at t equal to 0, and at t equal to 0 the input is 0. Okay. So okay, you see that this is also the input line, this is also the input line. So I can just extend this, okay, like this. So now at t equal to 0 the output is negative, and if output is negative, what do we do? What is the rule? We have to compare the input with upper trigger point, and then the moment when input goes above upper trigger point, we have to make the output equal to positive. So now as time increases, input goes from here to here, so input is increasing, but up to this point output is not going to change because input is below upper trigger point. So input will increase, output will remain negative. Okay. So up to this point, so this is t equal to 0. After that, input is increasing, increasing and increasing, but output is still negative. At this moment, okay, so call this t0, call this t1. So this is t0. This at this moment t1, input is now increasing below upper trigger point. So therefore, the output will become instantaneously positive. It will go from negative to positive immediately. Okay, so this is how it will go. So output will become immediately positive, and then you see input is increasing further. But so this moment is again t1. This is t1. This is an instantaneous jump. Okay, to go from here to here, it takes no time. That's why I'm writing t1 here as well as here. It takes no time. But after that, let me call this point t2. This is t1, this is t2. So from t1 to t2, input increases. So I go from left to right. I come up to this point, maybe a little less. Okay, and then output stays at positive. Okay, so let me put an arrow. Okay, after that, what happens? Input goes down. So up to this point, t3. Okay, so then input is going down. So let me put a reverse arrow, but output will remain positive, because output, now the output is already positive, and when the output is positive, what is the rule? I have to compare it with the lower trigger point, and the input is above lower trigger point, so output will remain positive. So now I will move like this. Okay. Okay, so I will move now like this, and the input will come here at this point, call this t4. At time 4, t4, when the input goes below lower trigger point, then output will come to negative again. Okay, and then if this is t5, after that input decreases, output will remain same. Okay, and then input increases, but output will remain positive, and it will remain positive until and unless at this point t6, when input crosses upper trigger point again. So up to t6, I'll go like this. So okay, so I forgot to write this times. So this is t4. This is the time when input goes below lower trigger point. So this point is also t4. Okay, t5 is this point, and t6 will be this point, same as t1. Okay, so this is how the input is changing, and if I draw input versus output characteristic, this is how it looks like. So let me put these arrows how it moves. Okay, so as the input increases, let me summarize. As the input increases, output initially remains negative, then at some point it switches to positive suddenly, like this. Then input can increase. It can increase a lot. It can go a lot, as much as you want. Okay, you can actually increase it a lot, but the output will not change. Then you decrease the input, output will not change. You decrease it for up to this, no problem, output will remain positive. You bring it here, that means at 0, output will remain positive still, but you make it negative, sufficiently negative, below lower trigger point. At this point, output will go to negative value suddenly, like this. Then you decrease the input, no problem, output will not change. You decrease, 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 no problem. Then you increase, 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 come here, output will remain negative. You increase further, yet output will remain negative. You come here, 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 up to this, no problem, no change. At this moment, it will go positive again. So it moves like this. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. Okay, so this is how the input output characteristic of a Schmitt trigger looks like. Input output curve characteristic, whatever you call, graph of a Schmitt trigger, Schmitt trigger. I never remember this spelling correctly. Okay, and you see this looks like a hysteresis band. This is called a hysteresis band, hysteresis loop. Okay, of a like a magnetic material. Okay, so for a magnetic material also it looks, that's continuous, that's smooth. Here it's discrete, but it's similar. That's why we draw the symbol inside this Schmitt trigger. Okay, this is how the input output characteristics look like. Now next thing is, okay, not next thing, this is most important thing. Okay, also let me also take a quick exercise. So a small exercise for you. Can you draw the input output characteristic of a comparator? Of a comparator. Okay, output versus input. How will that look? Comparator, for the comparator, normal op-amp based comparator, which you have shown here. Can you do that? It's simple. I'll just tell you. It will just look like this. Okay, so, and if you want to put arrows, you can put the arrows like this. So this is for a comparator, and for Schmitt trigger, it is like this. Okay, and let me put arrows. So you observe, if you so, and what is this value? This point here. What is this point? This is nothing but the lower trigger point. Okay, so this is input equal to lower trigger point, LTP, this point, and similarly this point is what? The value of input is equal to upper UTP. Okay, so here also this is UTP, this is LTP, lower trigger point. So you observe that if you can change the lower trigger point and upper trigger point and bring them closer, okay, if you bring this line here and bring this line here, then this gap reduces. Okay, and this gap is called, it has a name. So this gap, this is called hysteresis band. Okay, which is same as upper trigger point minus lower trigger point. Now, if you make upper trigger point equal to lower trigger point and both equal to 0, then this will become like this. So, this is a special case. You can think that upper trigger point is equal to lower trigger point is equal to 0. This is 0 volt. Okay, great. Okay, now let's come to the main question. So let's go back. We have seen that. What are you studying? Okay, by the way, what are you studying? We are studying frequency meters. Okay, and how does a frequency meter works? If we give some square wave input to the clock of a counter, and the counter counts the number of edges, and but if the input signal is not rectangular, then we have to convert the rectangular say the sine wave or any other wave into rectangular wave. So that's what we are studying, how to convert a sine wave into a rectangular wave. And we have seen we can use a comparator, fine, no problem, but if the input is noisy like this, then we run into problem, because we get false edges, wrong edges. And then we said we can solve this problem using a Schmitt trigger. Okay. Now let me just tell you how does this Schmitt trigger solves the problem. Okay. So for that I will use this. So what are we discussing now? So we are discussing how a Schmitt trigger helps against noisy input. Okay. So if the input signal is noisy like this, so this is an ideal sine wave, but say the input signal is actually like this, it's noisy. Okay. And let me make it a bit more noisy. Okay. So if we had used a comparator, so this is the noisy input. Now if we had used a comparator, then the output would have been like this. So let's just consider at this point, okay, only at this point. So here you see for a small region the input is above 0, so output will be positive. For the small region, then it will be negative. Okay, fine, no problem. But before that, here it's negative for a small part, and before that it's positive. Okay. And so instead of getting one edge here, we are getting two edges. One is this, another is this, two falling edges. So count will increase by a factor by 2. So this is the output from a comparator, normal comparator. But how will be the output of a Schmitt trigger? Okay, say let's assume here at this point the output of this Schmitt trigger. So let me just write output from Schmitt trigger. Say here it is positive. Let's start with the assumption that we start we have the output equal to positive here, okay, because the it's a normal assumption. I mean, it's logical because the input is sufficiently high, it's even above the upper trigger point. So definitely at this point the output will be positive, okay, because the input here is always above the upper trigger point. So we start from the assumption that here the output is positive. How long will it remain positive? It will remain positive as long as the input doesn't go below the lower trigger point, because output is already positive. So I have to compare with the lower trigger point, okay. So now this lower trigger point is the active comparison boundary. This is inactive. Upper trigger point is inactive at this point, okay. So I have to compare only with the lower trigger point. So when does it go below lower trigger point? It is here at this point, okay. So up to this point the output will remain positive, and then it goes to negative. So it comes here. Now how long will it remain positive? It will remain positive as long as the input is not crossing the upper trigger point. Now let me just increase the level of noise a bit. So let me make the input more noisy. I can make it even more noisy. Okay, so you see we have a lot of noise, but will the output change here at this region? No, because you see, okay, let me make it even more noisy. So you see, once the output has gone to negative value, then the lower trigger point is of no use. It is not active. The comparison will occur starting from here with only with the upper trigger point. So this is the active comparison region after this point. So even if you see the input is actually crossing the lower trigger point several times, here going up above the lower trigger point, going down the lower trigger point, it's crossing the lower trigger point, but now the lower trigger point is not active. So we are not comparing with the lower trigger point, we are comparing with this level, right. So therefore the output will not change here, output will remain negative, okay. Even you see I have made the noise so high that the input is going above 0 level. Here it's crossing the 0 level, but still output is going to stay at negative because it's not crossing the upper trigger point, right. So no problem here, okay. Similarly you may also consider this region. You see the output is positive, so therefore the active comparison is between lower trigger point and the input. So even if the input is oscillating as around the upper trigger point or the 0 value here, output is not going to change. So the output only changes once here, okay. So output changes only once here, and that's what we want, because I mean, for this signal you can consider here to say here to here one cycle, okay. Starting from here to here, this is one cycle. So we should have only one edge somewhere near here and one edge somewhere near here. But if we use a normal comparator, we are getting 2 edges here, or we may get more edges depending on the noise. But the Schmitt trigger is ensuring there is only 1 edge here. So that's how the Schmitt trigger helps in proper counting in a frequency meter. Okay, so this is fine, this is not fine. Okay, so what do we have to then do? We have to do this. So if this is my count, so going back to frequency meter, this is what we are starting now. So what we have a counter, it has many bits, it has the input clock, it also has the reset. So this is the clock, and what did we do? We had a AND gate before this, which is used to stop the counting after some time, after some pre-specified time. This is the gate signal, which determines how long to count, and here we had the input. Now instead of applying the input directly here, we will have the Schmitt trigger before it. So the input actually will be here. So here we can give sine wave, triangular wave. They can be noisy, so they can be noisy like this. But here it will become a non-noisy rectangular wave with the frequency same as the frequency of this input signals, which can be noise. Okay. Thank you, and let's study this more in next class.